This is Math 432, Applied Combinatorics. I am Professor Asaf, and today we're going to be talking about seating charts again, but in a very different way. Recall that previously we asked, in how many ways can we seat 9 people around a circular table? And we saw from the nice counting argument that we did, we could just assume that maybe Yoda is the head of the table, and then we can just line up who comes next, and these 8 people, other than the head of the table, are all arranged in any line, and then they just march in. So we saw that this was equal to 8 factorial. But if we want to add a constraint to this, so how can we seat 9 people around a circular table so that no 2 neighbors know one another? This is a very different problem. We're taking some really interesting information into account. It's now matters which people are which. So, for example, we can't have Han and Chewie sitting next to each other. So let's move over this guy. I don't think Han's ever met him. So now that's good. And now Chewie doesn't know the Emperor, so that's good. This fat guy, well, let's see. Let's break up Leia and Han. And, okay, well, Luke and Yoda know each other, but pretty sure these two never met because I don't believe in the prequels. These guys met when they were on the moon of Endor, and they had a little battle. So let's... we can't put Luke next to this. So you see what I'm doing? I'm trying to come up with a way to do... Well, no, those guys met because remember in the pit, this was the guy with the big monster. So we need to move him away from Luke. It's actually looking kind of complicated to do. So we'll talk about how hard this problem is. But first, let's try to figure out how can we actually do this in a systematic way instead of just shuffling the people around in the way that I've done it. And the idea is you need to represent this information that we have in some kind of useful way. And so what we're going to do is we're going to represent it with a graph. So the easier way to do this problem, the solution to this problem, is to represent the information that you have, which is the know one another. So represent relationships with edges of a graph. So that's the key. We're going to turn this into a graph theoretic problem because this sort of constraint is something that really ties these people together into a network. So how does that work? Well, suppose we only had 6 people. It's a little easier here. And we can say, okay, well, here are the knowledge relationships of who knows whom. So for example, we could draw a graph. If we were going to draw this as a graph, we could say, okay, Luke, who does he know? He's going to have, actually, this is going to be the doesn't know graph. So Luke doesn't know... Wow, he's really, I guess Luke is really the problem here. I think Luke doesn't know this guy, and maybe that's why we can't do it, because Luke knows too many people. So let's just chuck him out for a second. He was sort of not the main character of the series anyway. Everyone knows it's all about Han. So, Han, who does he know? Well, he doesn't know this guy or this guy. He didn't meet the fat guy because he was still frozen in carbonite. He knows Chewie, doesn't know the Emperor. So he's got a lot of edges. Okay, and that's how we would represent it. So now let's just focus on this. Suppose that we have an edge here. So what do the edges mean? So edges means strangers. So every edge represents a stranger. So now what are we doing? We want to sit people next to each other. Well, let's start with the red guy and say, okay, well, let's start with the red guy. Who could he sit next to? Well, he could, for example, sit next to the blue. And who could the blue sit next to? Well, blue, for example, could sit next to the black. And black, who could he sit next to? For example, he could sit next to the green. And who could green sit next to? Orange. Who could orange sit next to? Orange could sit next to purple. And who could purple sit next to? Aha! Purple could sit next to red. So now if we move our model out of the way, we can think about how we can represent this, the solution. So what we did is we figured out that we start with red. That was how we did it. We had red, and then we said red sat next to blue. And I can just look at this graph here, just the highlighted edges that are darker, to know, okay, I've got the blue over here, and red is also next to purple on the other side. Who are purple's neighbors? Purple's neighbors are red and orange. And who are orange's neighbors? Purple and green. Green is adjacent to orange and black is adjacent to blue and green. So this isn't necessarily the only way that I could have done it, but basically taking this star and stretching it out into a circle, here's what I've got. And this is an example of a Hamiltonian path. So this is why we look for Hamiltonian paths. A Hamiltonian path is a path on a graph. So we're going to be going from vertex to vertex across edges. And now we don't care about using edges. We don't care about which edges we use. We care about the fact that we hit each vertex once. So we want to touch each vertex once and only once. And you can see that, of course, that's going to mean we'll never use the same edge twice, but it's a more restrictive condition. And this idea of finding a Hamiltonian path is a very interesting one, and it's very different from the Orlarian walks that we looked at before. So let's just talk for a second about the difficulty of problems, and we'll come back to finding Hamiltonian paths and Hamiltonian cycles. Let's talk about the class of P. P is a class of problems for which a solution can be found in polynomial time. So what's an example of this? So an example is an Orlarian walk. Orlarian walk. So remember, for an Orlarian walk, what does this mean? This means that when we had a graph, we wanted to trace the edges, the edges of the graph, so that we hit each edge exactly once. So we can go maybe 1, 2, 3, 4, 5. This would be an Orlarian walk. It doesn't end where I started, but it's still a walk. It's just not a cycle. So this is an Orlarian walk, and we can find one. We saw that we can find one, and it's actually polynomial. The amount of time it takes is actually linear in the number of edges. So we can find an Orlarian walk easily in the graph, and how hard it is, how much time it takes, is just a linear function of the number of edges. Let's compare that to another class, which is NP. NP is the class of problems for which a solution can be checked in polynomial time. So what's an example here? An example here would be a Hamiltonian path. So if I give you a Hamiltonian path in a graph, so say I had a graph like this, and I can say, okay, can you just check for me that this 1, 2, 3, 4 is a Hamiltonian path? It touches every vertex exactly once. You can check that, and the complexity of doing it is linear in the number of vertices, right? You just walk through the path, and we know the path is going to hit every vertex exactly once. If it hits one more than once, we go ahead and stop, and if it doesn't hit them all, then we've stopped prematurely. So it's certainly going to be linear in the number of vertices. And a big problem in complexity theory, and one of the Clay millennial problems that's still unresolved, is whether P equals NP. So if a solution can be checked in polynomial time, does that mean a solution can be found in polynomial time? Most people believe P does not equal NP, but it's still not yet known. The problem of finding a Hamiltonian path is something that's known as NP complete. This is as hard as it gets, and any hard problem in this complexity theory sense is equivalent to the problem of finding a Hamiltonian path. So when we're looking at things like Orlarian walks, we had nice constructive proofs and we could actually do it. Hamiltonian paths, whenever we prove an existence proof, it's usually not going to be constructive, and it's probably not going to be efficient.